Welcome to the second class of the course. So before we start, I have a couple of announcements. The first one is that there was actually a misunderstanding between me and one of the people working at the university. So basically, I was scheduled to have 16 classes of 1 hour and 45 minutes each. However, I later realized that basically this was too much, and so actually the course is of 15 classes of 90 minutes each. So these are the new dates, which if you check against the old dates, you'll notice that the only difference is that the last lesson in June was suppressed. So the class on the 30th of June is actually cancelled, and there is only a total of 15 classes instead of 16. And also the classes are of 90 minutes each. The second announcement is that there was a technical issue. So basically, when I was uploading when I was rendering the last video, the second part, which was roughly 45 minutes long, I realized that I had to lower the quality to 720p because I was exceeding the 250 megabyte limit on Moodle, as I think that 720 is too low for video quality. I think 180 is better. I think I will split each class of 90 minutes into 3 videos of roughly 30 minutes each. I apologize if this causes any inconvenience to you, but I think it's better to have videos of higher quality where the text is actually legible rather than smaller videos and not having the inconvenience to jump from one to the other. So okay, let's move on with the class. And as promised, last time we were left with Hilbert spaces, with the recap on Hilbert spaces to do, and so let's start with that. Just as a reminder, I have written a little hierarchy here. So Hilbert spaces are a less general notion than Banach spaces, which we saw last time, which in turn are a less general notion than complete metric spaces or metric spaces in general. And metric spaces are also topological spaces. So these are the inclusions. So this is the hierarchy basically between the functional spaces that we saw. Okay. So before talking about Hilbert spaces, we have to introduce inner product spaces. So let H be a real vector space, a function which we denote by these 2 brackets, from the product of H times itself into R is called an inner product if these 3 properties are satisfied. So the first property just says that the inner product is symmetric, as it happened with the distance, for example. The second property says that the inner product is bilinear. So here the bilinearity is actually expressed only in the first variable of the inner product, but you see that if also symmetry holds, then actually it is sufficient to ask linearity in the first variable, because then by symmetry you also have linearity in the second variable. In any case, bilinear means that this function is linear as a function of both arguments, so in the first and in the second argument. The third property is called positive definiteness, and it means that if you take the inner product of x with itself, you always have a quantity which is larger or equal than 0, and x against x is equal to 0 if and only if x is 0 itself. Okay, if H and this bracket satisfy these 3 properties, then the pair is called an inner product space. Okay, remark, if you have an inner product space, then you can define this function here as just the square root of the inner product of x with itself. And this function here actually defines a norm over h. So hence the first inclusion in the hierarchy here, meaning that if h is a inner product space, then h is also a normed space, and in turn a metric space and a topological space, as we saw last time. Okay, in inner product spaces there is a pretty fundamental inequality holding, which is called Cauchy-Schwarz inequality, which just says that the absolute value of the inner product between two elements of H is less or equal than the norm, than the product of the norms of the two elements, and where the norm is intended in this sense here. Okay. So, having said that, given an inner product space, we say that H is a Hilbert space if H equipped with this norm here is complete as a normed space. Okay, so it means that every Cauchy sequence is converging to some element of X with respect to this norm here. Okay, so now let's introduce the concept of basis, which is very useful in many applications, because as it turns out many Hilbert spaces admit basis. So let H be Hilbert, a set of elements En containing H. En here is intended to be countable actually. Okay, so n ranges into the natural numbers. So this collection here is called a basis for H if the elements of this set are orthogonal, meaning that Ei times Ej is 0 whenever I is not equal to j, and okay, sorry, here I should have added, because for basis we mean something which is actually orthonormal. So this should be equal to 0 if I is not j, and also Ei times Ei has to be equal to 1 for all i's. Okay. So having said that, so if this orthonormality condition holds, and the span of Ej is dense in H, so meaning that the closure of this set is dense in H with respect to the norm induced by the inner product. Okay, we for span of a set, of an arbitrary set A in H, we mean this set here. So it's just a set of all the finite linear combination of elements in A, not in H, of elements in A where the linear combinations are taken with respect to scalars in the field R, and these are finite. Okay, so you take finite linear combinations and then you close this set with respect to the norm, and you should get the whole H. So we have this theorem. If H is a Hilbert space which is also separable, then it exists a basis, so an orthonormal set of vectors such that the span, the closure of the span, is the whole space. Okay, notation, since we have a basis we can define coordinates. So given a basis of a Hilbert space and an element of the same Hilbert space, we define xk as the inner product of x against ek, the kth element of the basis. And we call this one the kth coordinate of x with respect to the basis En. Okay, so as it happens in Euclidean space, whenever you fix a basis, then you have some properties. So you can express a vector in the Euclidean space as you can decompose it with respect to the basis. Okay, so in RD you can write something like this: xj ej j equals to 1 from 1 to d, where ej is this vector, right? So it's all zeros except 1 at the jth place. Okay, let's delete this. That could be confusing. Okay, so the proposition, as I was mentioning, is something similar to what happens in RD. So if H is a Hilbert space with basis En, then number 1, the square norm of a vector V in the space is just the series of the squares of the components of V with respect to the basis. And also if you take the inner product of two elements of the Hilbert space, then this is just the series of the products of the components. Okay, and these are actually useful to compute inner products or norms whenever you know a basis in the Hilbert space you're given. Okay, as I was mentioning before, for a separable Hilbert space there is a natural correspondence between the space itself and L2, where okay, last time we saw LP, but just as a reminder, L2 is the space of sequences, so infinite sequences of real numbers, such that this series is finite. Okay, J goes from 1 to plus infinity. Yeah, and remember that L2 is a norm space with the norm given by this quantity here. And also in particular for p equals 2, so in the case of L2, we actually have that L2 is a Hilbert space. Okay, to see that H is equal to L2, is isomorphic to L2, we need the concept of convergent series. So let's say that X is a norm space and take a sequence in X. We say that the series of this Xn converges to some X0 if the partial sums converge to X0 as n that goes to plus infinity. So the partial sums are defined as for real numbers. Basically you sum the first n elements of the series and then you take the limit. Okay. Alright. So with this we have the following theorem. If H is a Hilbert space with a basis En and Vn is a sequence in R, then the series of Vn against En converges to an element of H if and only if the sequence of the squares of these coordinates here basically converges in R. So this is telling you that to check whether this defines an element of H is sufficient to check whether or not this series is convergent in R. And in particular, as a corollary that I didn't write, in particular we have that H is isomorphic to L2 where the isomorphism is given by the map that sends that sends a vector v in H into the sequence of the components. So let's write it like this: v1, v2, vn, etc. Okay, let's do some distancing here, and it didn't work. Maybe, yeah, more or less. Okay, another nice aspect of Hilbert spaces is that the dual has a very nice structure. So actually the dual of a Hilbert space H is isomorphic to H itself. So this is the famous Riesz theorem, which we state here. So let H be a Hilbert space and define the map phi, I think, from H into the dual, defined by as follows. So for an element in X, you define phi of X to be the linear operator, which obviously takes a value of H, takes an element of H, and outputs a real number. And this real number is just the inner product between X and Z, and this for all Z in H. So we have the psi is invertible and is also an isometry. So the norm of psi of X, the dual norm, is just equal to the Hilbert norm of X. Okay, so this is telling you that H can be identified with H star via this isomorphism. In particular, we have the weak star and weak topologies on H coincide, and also we can easily check weak convergence by testing against elements of H, because all the linear continuous functionals have this structure by the Riesz theorem. So xn converges weakly to x0 if and only if xn against z converges to x0 against z for all fixed z's in H. Okay, let's see some other properties of weak convergence in Hilbert, which is actually easier to handle than weak convergence in norm spaces. So let H be a Hilbert space with basis En. If xn is weakly convergent to some x0, then the coordinates of xn converge to the coordinates of x0 for each coordinate. Okay, and so I mean this is just an obvious consequence of this fact here, right? That because clearly the coordinates are linear continuous functionals. Okay. So we have here the first warning. So we already know that weak convergence does not imply strong convergence. This is not true in norm spaces, and it stays not true in Hilbert spaces, of course. However, I also want to mention that it is not true that if xn converges weakly to x0, then the norm of xn converges to the norm of x0. So this is saying that the norm is not sequentially weakly continuous. What we saw last time is that the norm is always sequentially lower semi-continuous with respect to the weak convergence. Okay, so you cannot expect also upper semi-continuity in general. However, the checking the convergence of the norms basically allows to relate weak convergence to strong convergence in Hilbert spaces. And this is summarized in this proposition here. So let H be Hilbert, so whatever Hilbert space, not necessarily separable. Then Xn converges strongly to X0 if and only if it converges weakly to X0 and it converges in norm, meaning that norm of Xn converges to norm of X0, which is different from saying that that this goes to 0, right? Okay, another useful proposition is that weak convergence can be tested against a dense subset. So let H be a Hilbert space and assume that Xn in H is a bounded sequence, which means that the supremum of the norms of these elements over all the elements basically is finite. Suppose that you have a subset of H such that the span of W is dense in H, meaning that its closure with respect to the norm is equal to the whole space. And also suppose that Xn tested against W converges to X0 tested against W for all W's in W and for some X0 which exists. Then one can see that Xn converges weakly to X0. So basically here we were saying that since the Hilbert space H can be identified with this dual, then weak convergence is equivalent to testing this convergence on each element of H. Here in this proposition we are saying that actually there is something better if you have a subset whose span is dense in H, and also you're supposing that the sequence is uniformly bounded, then it is sufficient to check convergence against only the elements of W to ensure weak convergence. This assumption here of boundedness is very important. You cannot remove it, and maybe I will give you an exercise in the exercise course to check this fact. Okay, a corollary, if SW, basically, you take the set En, where En is a basis, and you suppose that the sequence Xn is bounded, then if the components, the coordinates converge, you can also conclude weak convergence. Okay. So in this case, W is acting as the vectors of the basis, which obviously satisfies that the span is dense in H by definition. Okay, so this is let's see. The proof is take W equals to En. Okay, maybe we conclude this with a very basic example, because these are the functional spaces that we mentioned in the introductory part of the first lesson. So the first space is X, which is just a space of continuous functions on some interval AB, with AB in R, and with norm U infinity, defined as the maximum of U of X, or the absolute value of U of X as X ranges in the interval AB, and Y is the set of continuously differentiable functions in AB with this norm. So the one norm is given by U infinity plus the infinity norm of the derivative. Then it is easy to check that X with the infinity norm and Y with the one norm are Banach spaces, so they are normed spaces and they are also complete. And it is also easy to check that they are actually not Hilbert spaces. And maybe you can do this by exercise. And to the hint, let's see. Sorry, to change color. So the hint to prove this is that in an inner product space we have something called the parallelogram law. And the parallelogram law says that so if you take two vectors of the space, you sum them, then you take away the difference, the norm of the difference, then this is the same thing as summing twice the square norms of the vectors. So this is for each x, y in your space H, your inner product space. So okay, basically the strategy to prove that these are not Hilbert spaces is to show that if there was a scalar product inducing these two norms, then this identity should hold, and then you can conclude that, I mean, basically this is not possible. You get to a contradiction. Okay, so this concludes the revision of functional analysis, and we move on with the next part of the course. So in this next section we are going to talk about calculus in normed spaces, and the reference book is the book by Kesavan called Nonlinear Functional Analysis, a first course. I mean, the book is, I don't know if it's available in the library, but anyways you probably won't need it, since I will basically covering everything. So in the sense, all the topics that we need will be covered in this lecture. So okay, throughout the section we denote by x and y two norm spaces always. Also u in x will be an open set, and f from u to y is a given function. So our objective is to construct a theory of differentiation for maps that are defined from u to x. So remember that u is a subset of this space x. So okay, I mean, this would generalize the concepts of calculus 1 basically. So the theory of differentiation for scalar or vectorial functions in Euclidean spaces. So the first definition is a generalization of the definition of differentiability, and it goes like that. So I remember it just once. So in this case f, sorry, okay. So here f is a function from u into y, where x and y are normed spaces, possibly infinite dimensional. Otherwise we are not saying anything new, anything more than calculus 1 dimensional. Okay, and u is an open set in x, open with respect to the norm in x. So we say that a function f is Fréchet differentiable at some point u0 in u if there exists a linear bounded operator from x into y which we call a of u0, such that this holds. So this is saying that let's say, so close to the point u0, we perturb the point a little bit with some vector v in the space x, and this is saying that close to the point u0 you can approximate your function, so the value f u0 plus v, by this linear functional here, which is evaluated at v. Okay, so this and this is divided by the norm of the variation, which is v in this case. And so if the limit has v in norm that goes to 0, so along every direction of this fraction here holds, then we say that f is Frechet differentiable at u0. Okay, so the first remark is that sorry, let me delete this first. Okay, so the first remark is that if f is differentiable at u0, then the differential is unique. So there is only one operator which makes this condition true, if there exists one, and this is very easy to prove. You just suppose that there are two operators which satisfy star, so this condition here, and then just by basically triangular inequality, so you want to estimate the difference of, let's say, b of u0 is another operator satisfying this, so you want to estimate this guy here, b u0 in v minus a u0 in v, norm y, and now I mean you just want basically by triangular inequality you can estimate this with b u0 v minus f u0 plus v minus f u0 in y norm plus the same but with a u0 instead of b u0, and then of course I mean this first this first term here will go to 0 because when divided by v, because you're assuming that b u0 is a differential, and same for this one, so also the second term goes to 0, and in total you've shown that these two functionals here, linear continuous functions, coincide on v. Since v was arbitrary, then you conclude that they are the same. So there is only one Frechet derivative if it exists, and as a notation we exactly, so the notation is here. So if f is differentiable at u0, this a of u0 is called the Frechet derivative, or just the derivative of f at u0, and we denote it by like this. So in this case f dash of u0, f prime of u0, is a linear operator between x and y. So often when we want to evaluate this linear operator, we write something like this. So f u0 at v, this will be a value of y for every v in x. Okay, so maybe this is something important to notice. Although your function is defined a priori only on some open set u, the differential is actually a linear operator which is defined on the whole space. So although f is defined from u to y, the Frechet derivative is defined from x into y. Okay, and it has to be linear and continuous. Okay, so the first basic remark is that we are not doing something crazy, but this is a natural generalization of the concept of differentiability for Euclidean maps. So for example, take f from Rn into Rm. In this case, if f is differentiable, you know that that the differential is given by the differential in the Euclidean sense is given by the Jacobian matrix, right? Which is denoted like this. So df in U is just an m by n matrix whose entries are the partial derivatives of f as follows, as is written here. And you can check by exercise if you want that. I mean, if you suppose that this function f is differentiable in the classical sense, then you can show that this guy here, seen as a linear continuous operator, so df of u, you can see this as a linear continuous operator from Rn into Rm. Then this will be your Frechet derivative. So you can just set f of u, you set it to be df at u. Okay, so this is f dash. Okay. So now that we have the definition of differential in a point, we can also talk about C1 functions. So we say that f, which is always a function defined from u into y. So we say that this function here, if it is differentiable for every x, for every u0 in u, then you can define this map. So f prime from u into the linear continuous operators from x into y, which sends u in its corresponding Frechet derivative. So this operator here. So if f dash f prime is continuous, we say that f belongs to C1 of u into y. Okay, so it's a C1 map from u into y. And in words, we say that f is continually differentiable. Notice here that continuity is with respect to the norms. So u is a subset of x. So in this space here, we take the norm on x, and on this space here, we take the operator norm. So we ask that f prime is continuous with respect to these two norms. Okay, let's see a couple of simple examples, which will be basically many of the actual examples we will see are of this form. So the first example is for f, which takes values, taking values in R and defined on some open set inside a norm space. So in this case, if f is differentiable in the sense of Frechet at some u0 in u, then the Frechet derivative is a linear continuous operator from x into R. So in other words, it's an element of the dual. Okay, so if f is now differentiable in the whole open set u, then we can define the map f prime from u into the dual. So as usual, by sending an element u of u into the corresponding derivative, which is an element of the dual in this case. The second example is for Hilbert spaces. So we always have f from u into R, where in this case u is an open set in a Hilbert space H. And in this case, we have that if f is differentiable at u0, some u0 in u, of course, I forgot to mention. Okay. Then we know that f prime of u0 belongs to H. Okay, so here also again, maybe this is not very clear. Sorry, let me think how to say it. I mean, belongs to H in a sense. That's what I want to say after. So f prime is just a functional. So it's linear continuous from H into R. Okay, we saw last time, actually, yeah, in the previous video, the Battery's theorem. The dual of H admits a nice characterization. So it just says that H is isomorphic to its own dual. And so by means of this characterization we see that there exists a point z0 in H such that f dash of u0 evaluated at some w in H is just a scalar product between z0 and w. And in this case we call z0 the gradient of f at u0. Okay, in analogy with the Euclidean case. So basically this is just a notation. This is not actually a gradient operator, but yeah, it's just to denote this differential basically in the case when we are in a Hilbert space. Okay, so let's see this first proposition on Frechet differentiable functions. So analogously to the Euclidean case, where if you have something differentiable, then you can show that it is continuous, and the same goes on for the same happens for the Frechet derivative. So assume that f is Frechet differentiable at some point u0 and u, then f is continuous at u0. Okay, so let's see. This is very simple, but let's prove it. So first of all, let's introduce this notation. We say that small o of some quantity, in this case the norm of v, norm x of v. So we say that some quantity is little o of something inside this argument if this holds. Okay, so if the quantity goes to 0 when divided by the norm of v, as v goes to 0. I mean, this is more general for notice that norm of v is something real valued by definition of norm. So more in general, we will say that ot to the power of n is something that goes to 0. Okay, this is horrendous. Goes to 0 when divided by t to the same power that appears inside here as t goes to 0. We will use this notation quite a bit in the following. Okay, so let's check continuity. So fix some point v in u, of course, such that u0 plus v is still in u. So let's make this a bit more precise. Let u, not u, let v in x be such that u0 plus v belongs to u. Okay, you can always I mean, we only need to check the continuity for points which are close to u0. So okay, if you really want to be very precise, since okay, we will do this only once just to make at least one proof very rigorous. So since u is open and u0 belongs to u, then remember we are in a metric space, so being open means that for each point inside the set there is a ball of some small radius which is entirely contained in the set. So then there exists some radius epsilon greater than 0. We have to move this. So since U is open and U0 is in U, there exists some radius, small radius epsilon greater than 0, such that the ball of radius epsilon and centered at x0 is contained entirely in U. And then let's just take V in this ball. Okay. So now we have just to show continuity, we have to estimate this difference here. And just by triangular inequality, let's add and subtract the differential of f at u0. So here, and then by triangular inequality, we have this the same differential appears a second time here. And so we know that the first term here by Frechet differentiability is little o of the norm of v, while for the second term we can use that au0 belongs to, so this one is, since au0 belongs to the linear continuous operators from x into y, and so we can just estimate this this bit here with the norm of the operator times the norm of the argument, so norm of v of x. And so, I mean, this is a constant, and this clearly goes to 0 as v goes to as the norm of v goes to 0. So in total we have something which is little o of norm of vx, which goes to 0 as v goes to 0. And this shows that as v is becoming small, these two terms here are approaching each other in norm y, so showing continuity. Okay, a second result is the chain rule. Okay, so the chain rule is, again, generalizing the chain rule for Euclidean spaces. So assume that you have three norm spaces, x, y, and z, u open in x, v open in y, and assume that you have two functions, so f defined from u into v and g defined from v into z. So suppose that f is differentiable at u0 in u, and g is differentiable at v0, which is just the image of u0 through f. Okay. So if they're differentiable, then the composition of g and f, which is a function defined from u into z, is differentiable at u0 in the sense of Frechet, and the derivative is given by this formula here. So the derivative of the composition at u0 is just the first functional, which is the derivative of g at the point v0, which is an operator from y into z, composed f prime of u0, which is an operator from x into y. So in total you get a linear continuous operator from x into z. And so whenever you have a composition, you can just compute the differential with this formula. Okay. So we will skip the proof of this fact because, I mean, it's something very similar to it's a very direct proof, something like the one we saw here for differentiability implies continuity, and maybe we'll leave it as an exercise for you to do in the exercise course. So I just realized that I said something inaccurate before. Here it said that v had to be in the ball b epsilon of u0. Actually, this is not what we need. What we need is that v belongs to the ball of radius epsilon and centered at 0, so that when you take the sum of u0 plus v, this belongs to the ball of radius epsilon and centered at u0, which is contained in u, so that f at u0 plus v is well defined in this term here. Having said that, let's go back to we were the chain rule. Okay, So next definition, we introduce some other concept of differentiation which is weaker than the Frechet derivative. As usual, f is a function defined from some open set in x into y, and we say that the function f is Gaussian differentiable at some point u0 and u in a direction v in x if the following limit exists finite in y. Okay, so let's see what this limit is. We're just so remember in the Frechet derivative we are doing this kind of variation, u0 plus v, so along all the directions in x. Here we're just moving along the direction tv for t belonging to r. Okay, so we're computing f in u0 plus tv and subtracting the value of f at u0, so a variation along the direction v, and then dividing this by the increase t. And so if this limit exists, we call this the Gaussian derivative of f at u0 in the direction v, and we denote it by this symbol here. So this notation is just the same basically as the Frechet derivative one. It's just the only difference is that we are adding a g here, so please be careful and not confuse them. So note, obviously, the same as the Frechet derivative, the Gaussian derivative, if it exists, is unique, and the proof is very straightforward. So we won't do that. So basically, as the Frechet derivative was the generalization of differentials in differentiability for Euclidean spaces, the Gaussian derivative is the generalization of directional derivative. Okay, for example, take a function from Rn into R and suppose that this is differentiable. Then if you try to compute the Gaussian derivative of f at some point u along the direction v, you can just see from this from this definition here that basically you just get the how is it called, the directional derivative of f along the direction v at the point u. And remember that, so this by definition in R, this is in Euclidean spaces, this is defined to be the directional derivative basically. And sorry, this is a bit unreadable. If f is actually differentiable, then if you remember, you can compute this directional derivative just by taking the scalar product of the gradient of f with the direction v. Okay, here we have a warning. So okay, this operator here, so f prime Gaussian at u0 is always linear from x into y. Okay, so this is something that holds in general. This is always linear from x to y. However, and this is a difference with the Frechet derivative, we are not requiring that this operator here is continuous. Okay, so in general we don't have that f prime g of u belongs to the linear continuous operators from x into y, but it's actually something that one needs to prove, okay, or require in general if you need it as an assumption. Okay, so there are two differences with the Frechet derivative. First, we're taking variations only in the direction of some vector v, whereas in the Frechet derivative the limit had to hold for v. If you remember here, we have v, and the limit has to hold for v that goes to 0, basically. Okay. And the second difference is that the Frechet derivative is by definition a linear continuous operator, while we don't require that for the Gaussian derivative. Okay, as you can imagine, the differentiable functions are also you can also differentiate them in every direction. It holds the same for Frechet derivative and Gateau derivative. So the proposition is as follows: if f is differentiable at some u0 in u, then f is also Gateau differentiable at the same u0 and in every direction. Moreover, the Gateau derivative at u0 coincides with the Frechet derivative at u0. Okay, this proposition is actually interesting because it's saying that so basically for the Frechet derivative you need to guess what is the Frechet derivative and then check that this limit here, oops, sorry, where is the definition? So you have to check, you first guess the operator AU0 and then you have to prove that this limit goes to 0, right? Instead, for the Gateau derivative is a constructive definition if you want. So basically you're saying if this limit exists for the direction v, then we say that this is Gateau differentiable. So basically this object here can be computed just by computing this limit. And if you happen to know that, so okay, so in practical examples, and we will see a practical example after this, basically if you want to discover if a function is Frechet differentiable, first compute the Gateau derivative and then check if the Gateau derivative is actually the Frechet derivative by plugging it into the definition of Frechet differentiability. Okay, and they have to be the same because if f was Frechet differentiable from the beginning, then you know that this identity has to hold. Okay, the proof again is very easy. So let's write down the definition of of Gateau differential. So f of u0 plus tv minus f of u0 divided by t. And here we can just basically we are dividing it by, sorry, we're first adding and subtracting f prime of u0 evaluated at tv. So here's the first one and here's the second one, and then we are multiplying and dividing this first fraction by the norm of v with respect to norm x of v. Okay, now this first bit here goes to 0, st, this first one here goes to 0, st goes to 0, because f is Frechet differentiable at u0. Okay, so, and here again this is going to 0, let's write a little remark, note, this is going to 0, converging in y, okay, to 0. And this because of the definition of Frechet derivative. And so we're left just with the second term here, and using that the operator f prime of u0 is linear, we can just cancel this t. And so we're left to the limit, we're left with f prime of u0 evaluated at v, showing that the Gateau derivative coincides with the Frechet derivative. Okay, a warning, as you might expect already, the converse of proposition 1.6 is not true. So Gateau differentiable does not imply Frechet differentiable in general. So for example, I mean, this is the same example or something very close to it that you were shown in calculus to see that if a function is differentiable in every direction, then it's not necessarily differentiable. Okay. So for example, take f defined like this for xy different than 0 and 0 if xy are equal to 0. So this is a function from R2 into R, sorry. Okay, then it is easy to check that the Gâteau derivative in 0 is constantly 0. Therefore, this Gâteau differentiable at 0 in every direction. Therefore, if f was Fréchet differentiable by the previous proposition, we would have that the Fréchet derivative, this should be equal to the Gâteau derivative, so this must be 0. And by definition of derivative, this means that of Fréchet derivative, this means that the limit as v that goes to 0 of f of v minus f of 0, here we are just taking u0 equals to 0, and by definition f0 equal to 0, u0 equals to 0. Then we're okay. Since you're assuming that f has to be Fréchet differentiable, this has to hold, so this has to be 0. However, if in the above limit we restrict ourselves to the direction along this parabola here, we find that by direct calculation using the definition of f, we find that this is actually this limit is equal to 1, which contradicts star. Okay, therefore f cannot be Fréchet differentiable at 0. Okay, I already went through this remark, I suppose, in a rather clumsy way before. Let's see, here's just as a reminder, proposition 1.6 is useful because it allows you to guess the Fréchet derivative of a function f defined from u to y, since the Gâteau derivative can be computed via a formula. And then you know that the Fréchet derivative and Gâteau derivative coincide whenever you are Fréchet differentiable. Okay, let's see a very simple example. As norm space, we take the continuous functions on the interval 0, 1 with the supremum norm, which we denote by this infinity symbol here. Then we define f like this. So f of u is the integral of the sinus of u of x in dx. Okay, so we ask ourselves what could be the derivative of f, or if f is Fréchet differentiable at all, and let's try to follow in the what I was saying before with proposition 1.6. Let's first compute the Gâteau derivative of f. So along a direction v, by direct calculation we have that this holds. So here I'm just really using the linearity of the integral and the definition of f. Okay, from the chain rule in R, basically, because these are is it in R? No, sorry, this by the chain rule, the general chain rule that we saw before, applying it to the function u plus dv. So u that goes into, no, not this function here, sorry, but to the function that sends t in u plus dv. Okay, so this segment here that at t equals to 0 is in u, and then passes from u0 in direction v. So this would be the direction v. Okay, so by chain rule you find that this none other than the derivative of a composition, and you find that easily that this limit is equal to this guy here. So the cosine of u of x times v of x, and this holds uniformly for x in 0, 1. Okay. Okay, since this happens uniformly, then we can, and the interval here is bounded, then we can pass to the limit, can pass this limit here under the integral, and compute that the Gâteau derivative is equal to this guy here. Notice that, as we were saying before, this is this function here, so this is not fg, is f prime, sorry. as we were saying before, we see that f prime of g of u is linear indeed. Okay. I mean, it shouldn't be a surprise. So let's change color. Okay, so this suggests that the Frechet derivative has to be the same as the Gauss derivative if f is Frechet differentiable. And so let's just check. Actually, no, I won't check it, but it is actually easy to check that this is true. So if you replace the Gauss derivative, again here I'm missing something, the Gauss derivative in the definition of Frechet differential, then you see that that indeed this fact here is true. So the Frechet derivative exists and is equal to this particular guy here. Okay, so question as suggested by this example. I mean, we saw we had this functional, and we saw that it was Gauss differentiable, and then by some miracle it happened that we could check by hand that the Gauss derivative was actually also the Frechet derivative. So the question is, when does this happen? What are the sufficient conditions for on f, such that if f is Gauss differentiable, then it is also Frechet differentiable? And okay, in order to answer this question, we need some machinery that we will see in a minute.